The universe is expanding 9% faster than it should be. That number comes from two of the most precise measurements in physics. Both are careful. Neither is wrong. They give different answers. Same universe. Two values. This is the Hubble tension. One number measured twice. The disagreement has hardened every year since 2024. Here is what it actually means. In 1929, Edwin Hubble looked at the light from distant galaxies and saw that it was stretched. The further away a galaxy sat, the more its light was stretched toward red. The conclusion was strange and exact. Every distant thing in the universe is moving away from us, and the further it sits, the faster it goes. The universe is expanding. The number that tells us how fast, the Hubble constant, is the most basic measurement in cosmology. Today, we measure that expansion two ways. The first way is to find a galaxy whose distance we know, watch how fast it is receding, and divide. That sounds easy. It is not. The universe does not put a meter stick next to galaxies, so we have to build one out of stars. Astronomers call it the cosmic distance ladder. It has 4 rungs. Each rung tells us how far away one type of object is. We use that to calibrate the next. The second way is to look at the heat left over from the Big Bang and read the expansion rate out of its imprint on the sky. We will come back to that. First method gives 73.0 kilometers per second per megaparsec. Second method gives 67.6. The gap is almost 6. The error bars on each are less than 1. The two numbers do not overlap. They have not overlapped for 15 years. The team that built the most precise version of the first method is called SH0ES. The principal investigator is Adam Riess. In 1998, he and 2 colleagues discovered that the universe's expansion is not just continuing, but accelerating. They received the Nobel Prize for that. A few years later, Riess started measuring the expansion rate itself, as carefully as anyone ever has. Here is how he and his team do it. Rung 2 of the ladder is a Cepheid variable star, a kind of giant star that pulses brighter and dimmer on a regular schedule. In 1908, Henrietta Swan Leavitt noticed that the slower a Cepheid pulses, the brighter it actually is. The pulse rate tells you the true brightness. Compare that to how bright the star looks from Earth, and you have its distance. Cepheids are bright enough to see in galaxies tens of millions of light years away. Rung 3 is a type IR supernova. When a white dwarf gathers too much mass from a companion star, it detonates. Type IR supernovae ignite near the same physical limit of stellar mass, and after a small correction for how their light fades, they release almost exactly the same total energy. They are called standard candles. Type Ia supernovae outshine entire galaxies for a few weeks. If you spot one and you know how bright it really is, you can read the distance to its host galaxy from how dim it looks. Parallax measurements give us distances to nearby Cepheids. Those calibrate Cepheids in galaxies that have hosted a type Ia supernova. Those calibrate the supernova. The supernovae take us out to galaxies far enough that the recession is dominated by cosmic expansion, not by local motion. Divide recession speed by distance. You get the Hubble constant. SH0ES has done this in 42 galaxies. Their 2022 answer is 73.04, plus or minus 1.04 kilometers per second per megaparsec. 1% precision, the most precise local measurement ever made. Now, the second method. Instead of climbing out from us, this one starts at the other end of cosmic history. At the moment the universe first became transparent, 380,000 years after the Big Bang. What you are looking at is the heat left over from the Big Bang. It fills the sky in every direction. The temperature is 2.725 Kelvin, and from one part of the sky to the next, it varies by 1 part in 100,000. Those tiny temperature wiggles are not random. They are sound waves, frozen in place at the instant the universe stopped being plasma and started being transparent. Built into those sound waves is a length, a ruler, baked into the universe in its first 500,000 years. The ruler is about 150 megaparsecs across, 500 million light-years. If you know how long the ruler actually is, and you can measure how big it appears on the sky, you can solve for the geometry of the universe in between. From that, a cosmological model gives you the expansion rate. That gives you the Hubble constant. From the other side, the European Space Agency's Planck satellite mapped the cosmic microwave background for 4.5 years. The final cosmological parameters came out in 2024. Their Hubble constant, derived from the imprint of those sound waves, assuming the standard model of cosmology, is 67.64 plus or minus 0.52 kilometers per second per megaparsec. That is also 1% precision from a method that depends almost not at all on the local universe. Both methods are careful. Both report uncertainties below 1%. Their numbers do not overlap. If the disagreement were chance, it would happen by accident less than 1 time in 3.5 million. Statisticians call that 5 sigma. 5 sigma is the bar a particle discovery has to clear. The Hubble tension is now above it. Until 2024, there was an escape route. The tension might just be a mistake in one of the 2 methods. People had a favorite candidate. Here is what happened to it. The most cited objection to the SH0ES result was that the Cepheid stars in distant galaxies might be visually blurred together with their neighbors. Hubble's vision is sharp, but not infinite. Crowding could make Cepheids look brighter than they are, and that would inflate the Hubble constant. In February 2024, Riess and his team published the first major James Webb follow-up. JWST sees the same stars at 4 times Hubble's resolution and 10 times the sensitivity in the infrared. The crowding hypothesis was rejected at 8.2 sigma. The mean photometry difference between the 2 telescopes was 1/100th of a magnitude. The Cepheid distances were correct. A second team had been quietly building a competing ladder. The Chicago Carnegie Hubble program, led by Wendy Friedman, calibrates supernovae with a different rung. Instead of Cepheids, they use the tip of the red giant branch, a sharp brightness limit at the top of an aging stellar population. Different physics, different stellar census, different host galaxies. Their 2025 combined Hubble plus JWST result is 70.39. Their JWST only number is closer to 69. Friedman and her team argue on the data that the universe does not need new physics. They argue the Cepheid ladder is just slightly off. In March 2025, the Dark Energy Spectroscopic Instrument released its second-year results. DESI is a robotic 5,000 fiber array on the Male telescope at Kitt Peak. Its job is to map nearly 15 million galaxies and quasars in 3 dimensions, and from that, measure the same baryon acoustic ruler. When DESI's map is combined with the cosmic microwave background and supernova, the data prefer a dark energy whose strength changes with time over a dark energy that is constant, at between 2.8 and 4.2 sigma, depending on which supernova sample is used. Not yet 5 sigma, but the strongest hint in a decade that the standard model of cosmology has a second crack. The same week, the Atacama Cosmology Telescope had published the final results of its 6-year survey. ACT is a 6-meter dish on a Chilean mountain. It is independent of Planck. Different optics, different polarization data. ACT's Hubble constant, combined with Planck and DESI's ruler, is 68.43, plus or minus 0.27. That agrees with Planck, in both temperature and polarization. The escape route through CMB instrumentation is closed. The early universe number is robust. Here is the part that keeps cosmologists up at night. Riess and Chicago Carnegie use the same James Webb Telescope on overlapping samples of supernova host galaxies, and they get different numbers. Riess gets 72.6. Chicago gets between 68 and 69.6. In April 2026, the Chicago group published an analysis showing that simply switching which low redshift supernova catalog you trust shifts the Hubble constant by 2 kilometers per second per megaparsec, 3.1 sigma. That is larger than either team's stated systematic uncertainty. Same telescope. Two careful teams. Two answers. The disagreement may not be between the methods at all. It may be inside one of them. If the Cepheid ladder is right, and the cosmic microwave background is right, the laws of physics in between have to give. Here are the candidates. Early dark energy adds a brief, exotic phase to the universe a few thousand years after the Big Bang. A quick burst of pressure that shrinks the cosmic sound horizon. A shorter ruler means the inferred Hubble constant comes out higher, closer to 73. It works on paper. The problem is that the parameters need fine-tuning, and Bayesian comparisons prefer the standard model unless you give it that. Alive, but narrowly. Evolving dark energy proposes that the constant dark energy in our model is not actually constant, that it might have been stronger in the past and is weaker now, or the other way around. A Hubble rate that descends with time can reconcile a local measurement of 73 with an early universe one of 68. This is what DESI is hinting at. The hint is real, but not yet a discovery. A local Hubble bubble proposes that we happen to sit inside a region of the universe that is roughly 20% less dense than average, a vast emptiness about 2 billion light-years across. Our local space would then expand faster than the cosmic mean. Some baryon acoustic data appears to favor the void. Most cosmologists do not. The standard model forbids density variations that large on those scales. The quiet possibility, the one that would resolve the tension without rewriting any physics, is that something about type Ia supernovae as standard candles is sample-dependent. The Carnegie Supernova Project and the Pantheon Plus catalog would then both be slightly biased in different directions. This is the simplest fix. It is also the hardest to prove. No proposal currently fits all the data. The cosmologists who run the conferences will tell you that in print and on the record. The crisis is not that we cannot measure the universe. The crisis is that we can twice, and we get two different answers. Hubble's original 1929 estimate had the universe expanding about 7 times faster than the modern value. We were wrong by a lot for a long time. The error bars shrank. The methods diverged. By 2015, 2 clusters were visible. 5 years from now, the textbooks will list one of these numbers, or a third one in between, and a new chapter of physics that links them. The Hubble tension is the first place to look. There are others. The gravity constant, the vacuum catastrophe, the lithium problem. All numbers that nearly line up. None that quite do. Which one next?